Good morning and good afternoon, everyone. As Katia mentioned, my name is Charlotte Bishop, and I am a project manager at MPA Satellite Mapping. Very interesting to do the poll beforehand as well, and I noted that the highest results were from lacking skill in geological interpretation as well as in data availability. So I do hope that my presentation helps to perhaps address some of those questions, or certainly if you have other questions, feel free to ask them at the end of the webinar or contact me directly, and I would be pleased to provide some more information. So my presentation today will show how MPA can use spectral information to support geological applications, with a bit of a kind of background on the spectral analysis side, as well as a focus on a case study which we undertook a couple of years ago now, which integrates both spectral data as well as full other geological information for a case study in Burkina Faso. So, MPA Satellite Mapping was founded in 1972. It was then purchased by Fugro in 2008 and subsequently by CGG in 2013. MPA's heritage has been focused on satellite mapping and value-added data service provision, with the company being set up shortly after the launch of Landsat-1. MPA provides services across a wide range of application areas, both onshore and offshore, and across a number of market sectors, predominantly exploration, but also including environment, engineering, and defense. Now part of CGG, which is a world-leading geoscience company, MPA can provide fully integrated geoscience services, providing complementary solutions to meet specific project needs. At MPA, we pride ourselves on being a completely independent supplier of all commercially available satellite missions. We don't own or operate our own satellites, but we are distributors or resellers for all of those commercially available solutions. So we're therefore able to provide trusted, unbiased advice on optimal solutions to meet the project needs, whether that's optical imagery, radar, or even elevation products. MPA provides support to one-off studies as well as longer-term monitoring or multi-client data solutions as required. These solutions are invariably tailored directly to meet the client's exact requirements, whilst also pulling in up-to-date advice and knowledge on new techniques and tools to improve the project or propose them for future project developments. The example that you see on the slide here just shows a Landsat base map merging into an interpretation across the same area, just to show some of the types of features we can extract. Satellite imagery has historically been used extensively for onshore geological applications since the launch of Landsat in the 1970s. As technology has improved, the increased availability of spectral information on satellites has provided far more information about the geology present in a region. All optical satellites measure reflectance, or emissivity if it's a thermal sensor, from the ground to generate the images that we see. Each feature we see has its own spectral signature, and there may be distinctive features about this signature which can help us to identify and map it using spectral analysis tools. The visible near-infrared, known as VNIR, and shortwave infrared, known as SWIR, portions of the spectrum are powerful tools for geology because they cover key absorption features of many geologic minerals. So whilst improving the visualization capability of the imagery, as we'll see later, improved spectral information also provides an opportunity to extract more information at a spectral signature level, which can support both lithological as well as mineralogical anomaly assessments. This in itself can be used in conjunction with interpreted structural features from an image to improve our understanding of the geological context. The example you see on the screen in front of you shows a Landsat base image with shading derived from SRTM on top of it, so you can see the topography quite clearly. It also shows the lithological outlines in white, and then structural interpretation, which is the black lines, blue lines, and red lines that you see on your screen. And the final interpretation is merging in on top of that, which shows the kind of GIS-ready products that we are able to produce from the imagery. Because the veneer and SWIR map absorption and reflectance of minerals, this allows us to be able to map surface alterations that can be associated with metallogenic ore deposits, which may take the form of deposit styles such as hydrothermal, epithermal, or porphyry style deposits. These types of deposits can help us identify copper, gold, and other metal commodities. However, we can also use similar techniques to look for rare earths and even for hydrocarbons, but that is for a different discussion. These types of deposits can help, the veneer is particularly useful for mapping iron minerals, whilst the SWIR has distinctive absorptions for clay and hydroxyl minerals, as well as carbonaceous minerals. The combination of both portions of the spectrum for geology provides us with a more complete information on the deposit style in an area. The more spectral information we have, coupled with the contextual geological information, the more we're able to interpret, and therefore the more confidence we can place on the results and the target areas that are generated. It is important to note that while spectral mapping can be used for geological applications, you're not detecting the ore body directly. There is no ground penetration from the satellite, as they are only measuring reflectance of what we see on the surface. And there is often no distinctive signature of the ore body itself. What we are essentially detecting are the indicator surface minerals, which will tend to exhibit a zonation pattern depending on the deposit style, which can help us indicate the presence of a potential ore body, which can then be followed up in the field. And you can see this from the diagram on your screen now, with the different zoning patterns and concentric circles away from the ore body, which is in the center. By integrating spectral analysis results with geological information such as structure and lithology, the results can be contextualized, false positives minimized, and a higher confidence and justification placed on the targets that are identified. Typically, multispectral satellite sensors such as ASTA, which has 14 spectral bands, Landsat, which has 7 spectral bands, are most commonly used for this because of the specific spectral bands that they have. More recently, WorldView 3 has come online, and with its similar band spacing in the SWIR to ASTA, but increased spatial resolution, there's certainly going to be some increased spectral mapping from it, and it provides scope for detecting smaller areas of anomalies with perhaps some more confidence. Whilst at present there is only one hyperspectral satellite platform suitable for mineral mapping, which is Hyperion, its coverage, as some of you may know, and quality is often very inconsistent. So for the time being, the lower spectral resolution solutions can be used, or alternatively, airborne hyperspectral imagery, if appropriate. There are now a wide range of airborne hyperspectral systems, and in contrast to the satellite solutions, these would typically have hundreds of spectral bands, therefore allowing unique spectral signatures to be extracted, which is not possible from satellite sensors at this time. Combining information extracted from imagery, as well as with geophysical information, where available, or other field data, allows us to contextualize the results better and provide targets with more confidence for further follow-up in the field. All of our spectral mapping is undertaken in MV. While standard tools are available within MV, MPA also have a bespoke toolkit for mineral mapping developed specifically by Excelis for MPA and then subsequently adapted by MPA to meet additional needs. When we talk about why spectral resolution is important, it's important to understand what it is we are extracting from an image. The plot that you see on your screen now shows a comparison of Landsat, ASTA, and hyperspectral data, just concentrating on the SWIR portion of the spectrum. In this case, the spectral signature that you're looking at is for the mineral alunite, which is often found in alteration zones. Here we can see that Landsat provides no distinctive features to help us identify this mineral from any other with a similar absorption pattern, because it only has 2 spectral bands in this portion of the spectrum. This is the orange line on your screen. The additional bands of ASTA, or even WorldView 3, which have very similar band spacing in the SWIR, provide some improvement to this, giving us a clearer idea of the shape of the spectra across its 5 spectral bands in this region, but still not allowing us to provide an exact match, bearing in mind that most hydroxyl or clay minerals have absorption points between 2.16 to 2.2 micrometers. In contrast, a hyperspectral sensor has many narrow bands and can therefore show much more subtle changes unique to specific minerals. Whilst hyperspectral is the ideal, its cost is often prohibitive for scanning large areas, and broadband analysis using sensors such as Landsat, ASTER, and now WorldView3 are commonly used as a starting point to screen an area, providing very important information on the potential of an area. It can be hard in some cases to understand the benefits of spatial versus spectral resolution. Particularly for satellite, it may come down to a trade-off between high spatial resolution but lower spectral resolution, or lower spatial but higher spectral resolution. And this will really come down to what you're trying to achieve from the project that you're undertaking. This slide hopefully goes some way to show what the advantages might be from a visualization point of view. The image on your screen now is a 0.6 meter resolution QuickBird image. This shows high spatial detail, but this dataset only has 4 spectral bands, shown here in natural color. However, if we have a dataset with an increased spectral resolution, albeit at a lower spatial resolution, suddenly our ability to increase the information we can extract even from just visualizing the images significantly increases and gives us a completely different viewpoint of the exact same area. I'll just flick between those again so you can see that. MPA undertake a step-by-step process to mineral exploration activities, which normally includes the following initial steps. Visualization, where the spectral band combinations are selected to optimize the features of most interest. Here, a composite has been defined to highlight alteration as pink features, so you can see there's quite a lot of pink on that screen. Initial processing, including ratios and principal components to identify initial areas of potential anomalies, and then subsequently noise reduction and end member extraction for the more detailed spectral mapping and classification. The general process here is applied to either satellites, so ASTER or WorldView3, etc., or hyperspectral datasets. But the process may vary slightly depending on the deposit style or the land cover in the region, as it may mean that some tools and algorithms we may use are just not going to be appropriate. And the process will therefore be tailored to optimize the results for the different areas. You will also see 2 plots on the screen. I must apologize that the background of them is quite dark, but hopefully you can see these reasonably clearly. At the top we have kaolinite, and at the bottom we have chlorite. And what this is showing is extracted spectra from the image itself, which in this case happens to be a HIMAP image, an airborne hyperspectral image. And that spectra extracted from the image is in white, so we can see that tracing around, and it's in comparison to the red, which is the reference library spectra. So we're expecting there to be a reasonable match between the two, and this gives us confidence to what we are extracting from the image. We can do the same with the broadband analysis, but of course we won't see some of these very subtle features, but we can still get a good indication of where key minerals might be or mineral groups might be. And the same again with the chlorite at the bottom, which is often found in alteration areas. We can see the red line being the reference and the white being the spectra extracted from the image. Once the spectral processing is complete, it's important to contextualize the results in terms of the geology, which allowing us to overlay the spectral results with the lithological and structural information to generate target areas. The right-hand image shows spectral results of the argillic, so clays and hydroxyl minerals, and carbonaceous minerals, whilst the right-hand image shows how some of the anomalies identified correlated well with the volcanic intrusions identified from the geological assessment, which could be inducing the alteration that we are seeing. This just helps to add confidence and support to the proposed targets identified. Just looking at the spectral results by themselves is often not really very helpful, and or indicative of what's actually happening in an area. Target areas are then generated from all of the results, providing a level of justification or confidence to their selection. In our case, we tend to rate the category of the confidence of the target areas. So we may have red areas are often our highest target areas, and then yellow may be slightly lower confidence based on the other information we have. These areas are then intended to be followed up with a field survey, which ideally would include a handheld spectrometer study of the areas identified to validate the findings. But it doesn't always have to, and this can still be used without that. Examples of some of the results from a field survey and the plots that can be achieved and that can be made, are shown on your screen now. So you can see the top plot, which just shows a traverse across a deposit and the different minerals that have been identified, which are all color-coded. And then the bottom plot shows the different extracted spectra that have come from the handheld spectrometer device. However, whilst this can be used without field survey, this additional verification really does add the validity to the process and also to confidence to the clients that these remote sensing techniques can work effectively. So it is something we would always stress is an important thing to happen. The remainder of the presentation focuses on a case study undertaken by MPA for Endeavour Mining in Burkina Faso. It particularly focuses on gold mineralization. This study focused on 2 license blocks in Burkina Faso, as you'll see from the map that gives the general location of where these are. The Yuga block, which is to the south, the blue one to the south, which has an existing gold mine, and the Bitu block, which is the northern block. This area is already known to be part of a kind of quite extensive gold deposit, and therefore it was essentially trying to find out what other potential there might be in this region. This is particularly important for the northern block, where they hadn't found any viable targets, as well as in the southern block to see if there was any more extension to the southeast of where their mine is, southwest of where their mine was. The process here incorporated a range of data sets and interpretation layers, including new satellite tasking of WorldView 2, as there was no stereo imagery in archive, and the client particularly wanted a high-resolution DEM to support some of their logistics and planning activities, as well as for detailed geological mapping. There was also generating the elevation model from the stereo, the high-resolution ortho image, spectral processing from Landsat and ASTA, regional structural interpretation at 1 to 50,000 scale, which in this case was from Landsat, and detailed structural interpretation at 1 to 10,000 scale, which was from the high-resolution WorldView 2. In this case, we were also very lucky to be able to be provided with a range of airborne geophysics information as well from our client, which included magnetics and radiometrics. And then there was a subsequent field study at the end of the project as well. Whilst the same process was applied to both blocks, the focus of the next few slides was on the southern Yuga block. This slide shows a series of supplementary data sets and some of the key results that were generated in this study. Firstly, the data sets that were used are presented. Here we see the SRTM DEM. It's important to say first off that elevation model as well as multispectral data for geological analysis is really very important to give us the viewpoint of the topography to help with not only with the structural interpretation but also with the lithological boundaries. This was then complemented with the higher resolution 1 meter elevation product, which was generated from the stereo data. You will note the mine which appears in the north of the area, which is has occurred since the SRTM DEM was produced in 2000. In addition, the low resolution image data sets of Landsat, so this is a 15 meter pan-sharpen product, and then the ASTA, which is shown here is a 30 meter product. And then the half-meter WorldView 2 also image, which was used for the detailed structural interpretation. Unfortunately, because this was a new collection, you'll see we did suffer with a little bit of cloud in this area, but it didn't hamper the interpretation too significantly. These results were then processed and combined with the supplementary geophysics datasets to derive the following layers, including the spectral processing, which was just from the imagery. You'll see here it's quite noisy with a lot of results. So the red is mainly the focus of the clays. We did have a bit of a problem in this region because of vegetation. So you do see some edge pixels related to vegetation, but these are masked as much as possible and then thresholded and tweaked. You see quite a big response over the mine itself, which is what you would expect because you have tailings dams as well, so you will pick out some of these similar minerals. But we do start to see some patterns, and when you zoom in more detail, you can see some of these features in more detail. The green areas are carbonaceous minerals in this case. The geophysics used here was useful as a radiometrics, which is shown in your screen now, helped to identify the sedimentary accumulation enriched in the rare earths, which is where the gold was hosted, rather than in the basement, as well as helping us to pick out the major structures and cross-cutting dikes on the magnetics, which helps to validate the structural interpretation that we see on the surface and how this relates to the structure that we're seeing at depth from the magnetics dataset. All of these layers help to provide useful additional information to allow us to draw conclusions on the potential for more targets in these areas. The more information we have, the better and more confident we can be in the output. This slide focuses on the detailed interpretation from the high-resolution elevation model and subsequent high-resolution image. It shows the elevation product which you've seen previously, the ortho image, and then the 1 to 10,000 scale detailed interpretation, which shows quite a dense spread of lineaments across this region. This slide is quite a useful comparison showing the detailed interpretation, this time as the red lines, in comparison to the regional interpretation at 1 to 50,000 scale, which was from the Landsat, with the black lines, just to show how much more information we can get from the higher resolution data sets. So it really does come down to the level of detail and the information that you require as to which might be the most suitable. Across the existing ore zone, which you can see here on your screen, we can see that without the high resolution we would not have seen the narrow lineament features that are present because there are no, these weren't picked up at all on the regional interpretation. And these were then checked in the field as well. And we can see the same fault structures running straight through the ore zone that we're seeing, as well as across the base of the pit, and also then subsequently through the pit walls where we're also seeing shifting. To give a bit of a kind of geological summary to this particular example, in terms of geology, it's been possible to map 4 main fault trends in this region. It's also been noted through the interpretation that the deformation history has affected the development of the sedimentary basin, which has made it more challenging from a spectral perspective. However, some minor clay alteration was identified in association with the Tarquinian Arco sequence, which provided some targets for follow-up in the field. The combination of the regional as well as the detailed interpretation allowed significantly more detail to be extracted to support the contextual geological analysis, as well as providing useful additional information on the local topography to support planning and access within these blocks. And just to provide a summary of the presentation as a whole before I open for questions. In summary, there's a wide range of satellite solutions to support geological analysis. Currently, spectral mapping can only be achieved from a very small number of satellite sources, but with proven capabilities for broad-scale anomaly detection. By combining multiple layers of information together with supplementary data sets, It adds confidence and justification to the anomalies identified, and validating this in the field is a really important step to highlighting the usefulness of these screening techniques to support exploration activities. While field surveys over large areas are not always possible in reality, the ability to quickly screen an area and then focus a field study more effectively can reduce risk and cut field survey costs to make it a more usable product, and providing with clients confidence in using remote sensing to support such activities. And thank you very much for taking the time to listen to me today.